everyone, welcome back. In this particular video, we will be discussing the problem. Find the number of bits to be flipped. What we are given is two numbers. What we need to do is write a program to count the number of bits that need to be flipped to convert the first number into the second number. It means, let's take the first number as 29. Let's take the second number as 15. So if I am saying first number is 29, second number is 15, let's represent both of these numbers in the form of binary system. So 29 as given in the explanation, it will be 11101, 11101. And when it comes to 15, 15 is being represented in binary as 0, then 4 times 1, 0, then 4 times 1. So we have to do what? We have to convert these bits into these corresponding bits. So if I just see that this is 0th bit, first bit, second bit, third bit, fourth bit. This is 0, 1, 2, 3, 4. Obviously, we are not writing more bits because all of them will be 0. All the remaining bits, if the number is a 32-bit integer, all the remaining bits will be 0. So no need to change in them. So which all bits do we need to flip from the first number to make it become the second number? We will say 0th bit will remain same, both are 1. First bit, that is the first index bit, since it is 0 here, since it is 1 here, we need to flip it, we need to make it 1. Second index bit, it is 1 here, it is 1 here, no change. Third index bit, 1 here, no change. Fourth index bit, it is 1 here, however it is 0 here, so change this also, that is flip it also. So since we need to flip 2 bits, answer is 2 only. As you can see in the output will be 2. 2 bits needs to be flipped. Flipped means toggled. Toggle means basically if 0 is input, output will be 1. If 1 is the input, output will be 0. But the point is how we can solve it, how we can calculate the number of bits which need to be flipped. One of the brute force solution, I am not saying brute force, I am saying one of the solution is that just do the corresponding comparisons from the 0th bit till the 31st bit. Check whether both the bits are same or not. And you can check whether a bit is set or not using a mask operation. I will discuss that checking whether a bit is set or not shortly, but let's assume you know how to check whether a bit is set or not. So 1 as well as 1, both are 1, both are set. So if both are set, no need to flip. So answer will remain 0 only. So initially we'll say answer is 0. Then next bit, here it is 0, it is not set. The check set bit will give you false. However, check set bit here will give you true. So since here it is not set, but we need it to be set, so answer will become plus plus. Next, second index bit is set in both the numbers, so no flipping required. Third index bit is set in both the numbers, no flipping required. Fourth index bit is set in the first number, but not set in the second number. So flipping required. So answer will become 2 and you will print that answer. Now the only point is how to check whether a given index bit is a set or not. So for that, let me take the same number 11101 and let's try to check it for the first, let's say second bit, and then we will check for the first index bit. So in order to check whether the second index bit is set or not, I have to first of all create a mask. How should the mask look like? Mask will have only the bit which we need to check to be set. All other bits should be 0 in that mask. That is what you will do is you will create a mask by doing what? By making a 1 bit left shift by the number of times you have to do it. That is 2 times in this case. So it will be 1 left shift. How many times? Bit number of times, whatever the bit you need to check. Once you have made this mask, what you will do with this mask is you will say that whatever the number is, let's say the number is n, this is mask, just do the AND operation between n and mask. That is, if you will do AND operation between them, wherever it is 0 in the mask, it will remain 0. No need to check for the first number because 0 and anything is always 0. But now since it is 1, whatever will be here, that will be in the output. Since it is 1 here, 1 will be in the output. And if you will say this number is having a 1 bit, it means this number is not 0. And this number is not 0, you can say return true. That is the number was having that particular second index bit was set. However, same test case, if I am just doing it for bit index 1, I need to check whether the first index bit is set or not. So first I have to create a mask. How I can create a mask of the first bit? Just have the 1 left shift by 1 place. That is, it will be this particular mask value, 1 left shift bit. and just do this mask and with the number. And if you will do and this time, zeros will always give you zeros in the and, but here also 1 and 0 will be 0. So this entire number, since it is 0, you can say there was no set bit at the corresponding index. So answer is false. Check set bit will give you false. So this is how you can check it for all the corresponding bits starting from 0 till 31, because there are 32 bits, and whatever the number of bits are different, that many you actually have to flip. This is one of the approach which you can surely use. And it is of course the most optimized solution. Why? Because it will just run the loop over all the number of bits. So if I'm assuming the number is n, number of bits can be log base 2n. However, if I assume that the number of bits are nothing but 32 only, so order of 32 will be order of constant. In this question, it is only 32-bit integer given to you. So you can either say logarithmic on the basis of input number, or you can say directly constant on the basis of 32-bit number system given to you. But the point is, we can do it in lesser code. Time complexity and space complexity will remain same, but we can write the same solution in lesser code by using the Kerningham's algorithm, which we have discussed in the last video. So if you have not watched the last video, you can try to code this using this particular solution only. But if you have watched the last video, if you have solved the last problem, which was based on counting the number of set bits in a given number using Kerningham's algorithm, we can basically do something in this. We can actually use one more operator, which is known as XOR operator. What will XOR do? XOR is nothing but such an operator where same bits, if you are doing XOR, XOR is usually written in the form of this caps like symbol. So 0 XOR 0 will give you 1. 1 XOR 1 will give you, actually different bits will give you 1 and same bits will give you 0. My mistake, my bad. Same bits if you will do XOR, it will give you 0. Same bits if you will do XOR, it will give you 0. Different bits if you will do XOR, 0 XOR 1, it will give you 1. 1 XOR 0, it will give you 1. So same bits on doing XOR, always output is 0. Different bits on doing XOR, always output is 1. How can you use this property? If I will do the XOR between both the numbers, what will happen is, if I will do 29 XOR 15, if I represent these numbers in binary, this is 1 1 1 0 1. XOR with the other number is 1, actually 0, then 4 times 1. So do the XOR bit by bit. So what will happen is 1 XORed with 0 will give you 1 because these are different bits. 1 XORed with 1 will give you 0 because these are same bits. 1 XORed with 1, 0 because same bits. 0 XORed with 1, different bits. So 1. 1 XORed with 1, same bits, so 0. So output will be this particular number. This will be certain number. You can say it will be, I guess, 2 plus 16. 2 plus 16 will be how much? It will be 18. So this number will be 18. But we don't need to do anything with that value. We actually need to do what? We actually need to count the number of set bits in this number. Why is it is so? If I will say that whichever bits were different in the both the numbers that are 1 in this XOR value, and that is what we need to figure out. We need to count how many bits were different so that we can flip them. We needed to flip this particular bit from 0 to 1. We needed to flip this particular bit from 1 to 0. And those bits are only 1 in the XOR number. Remaining all the bits are 0. So just count the number of 1 bits in this number using Kerningham's algorithm. What was Kerningham's algorithm? Let me just write it in one line. We always used to do, if the number, this number is, let's say, n, what we used to do was n is equals to n and with n minus 1. And every time if you will do this, one set bit will get removed. So the number of times you are able to do this till the point number becomes 0, that is the number of set bits, and that is of course the answer. So the coder, the smaller code which will use Kerningham's algorithm will be, first find the XOR of both the numbers, which we need to basically convert from and to, that is the first number and the second number. Do the XOR between them. Whatever the number will come, find the count bits or find the set bits in that number by using Kerningham's algorithm, which is n updated to n and n minus 1. And whatever number of times this operation is being able to done till the point n is not equal to 0, we will say just do count plus plus, and that count itself will be the answer, number of flips which we require. So this strategy will also obviously take the same time complexity, same space complexity. Why? Because in the worst case, all the bits can be set Actually, Kerningham's algorithm take that much time equivalent to number of set bits. And in worst case, we can say all the bits are set. So it will be logarithmic in terms of n, or it will be constant in terms of 32 bits. So what I am going to do is I'm going to write the code in terms of Kerningham's algorithm only, because it will not require any function to check whether a bit is set or not. We do not require any mask or anything like that. So let's write the instruction manual. First step will be calculate XOR of A and B and store it in a variable, let's say n, and store it in n. What we need to do is we need to maintain a count variable. So set integer count initially as what? Initially, we will start the count from 0. We will run the loop till this n value is not becoming 0. That is till all the bits from that number is not becoming 0. And every time what we need to do is we need to just remove one of the bits, one of the set bits actually. That we can do using the operation n is equals to n and with n minus 1. That is update the n with this particular value. But also do what? Increment count by 1, because the number of times you are able to remove set bits, that is the number of set bits. In first operation, if you will do this number and with n minus 1, what it will give you is 1 0 0 0 0. Next time, if you will do and of this number with the previous number, what it will give you is all zeros. So the number of operations are equal to number of set bits, and that is the answer 2 in this case. So increment the count by 1, and whatever the count is finally, that is our answer. So return that answer, return that count. So very basic code, but using the previous approach, that is the counting set bits in a given number. And what is that given number? It is not A, it is not B, it is XOR of A and B, because XOR is what which will give you the different bits set and same bits unset, or same bits 0. We will be writing the code for the problem. So first of all, what we discussed was we have to calculate XOR value. Let's store it in a variable n, which is A, XOR B. XOR is the operator. In Java, I am writing the code which is using this caps like symbol, which is on my keyboard above 6. So most probably in most of the languages, it will be similar. Then after the n variable we have declared, we will also set a count, which is initially starting from 0, because we need to count the number of set bits in this n number. We will do what? We will run a loop till this number does not become 0. Every time, just do the AND of this number with the previous number, that is n minus 1, and update the same number itself, that is n is equals to n and n minus 1. Whatever number of steps this loop will run, that is the answer itself. So return that count. So very basic solution. Let's just run it and see if it is working for the sample test case. 29,15 should give you output 2. Let's see. Actually, there is some small error. The inputs are in long, but we are creating int as the n value. Since we are doing XOR of two numbers which are 64-bit integers, n variable should also be 64-bit integers. Although count will remain integer because we have to return integer only. Count will be only 32 in worst case. So let's do the run again. Let's see if it is working for sample test case at least. And if it will work, then we will also submit. But it is taking some time to run. Let's see whether it will work or not. Actually, it is taking a quite lot time, more than what is usually expected. So let's wait for it to run. Or maybe let's do what? Let's just copy the code and refresh the website. Sometimes website can also be buggy. So let's run it again and see this time. So as you can see, 29,15, it is giving you the output as 2. So it is working as expected. Let's just submit it and see whether it is going to work for all the other test cases or not. And just by seeing it, all the 20 test cases are getting accepted. With that, we are done with the problem. Find number of bits to be flipped with the time complexity logarithmic, log of n, or you can say constant, because just the number of bits are 32 only in this question. So constant time and as well as constant space solution for the problem. Find number of bits to be flipped. Let's meet in a new video with a new problem. Till then, bye bye. Take care.